Yes, Abdullah. Yeah, you raise your hand.
I'm audible. Hello, Professor. I'm
Hang on,
audible.
the audio is really low. Let me see if I can raise the volume. Would you mind typing your question in the chat?
Okay.
Oh, okay. I think probably the best thing for the project is if you want to email me your code, I can take a look and then I can help you debug it that way. It's a little bit hard to kind of do it over Zoom like this. Um, yeah, or if you want to wait until next week, so Tuesday I may still have a little bit left to lecture. But if you want to bring the code next Tuesday, then I'll have open office hours and we can go over the code at that time too. Yeah, but fastest way would be to email me and then I'll get back to you as soon as I can. Yep. All right. It's 5:30. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. All right, so first order of business. I did grade your guys' midterms. Have them ready to return to you guys today. I wanted to finish it today just because I know some of you are going to the alumni event after this, and so some of you are here when you're not normally here, so I wanted to give the chance to give you back your midterms. So average on this exam was 38 over 50, which is a shade lower than the midterm one. So you guys are kind of performing right at the expected value there. Okay. One thing you might have noticed when I input your grades for midterm two, I might have swapped the value into the slot for midterm one, right? So if you recall from the syllabus, I know that was ages ago, but one of the policies I have in this class is that, between the two midterm exams, I choose the one that you scored higher in. and then I make that one a larger percentage of your grade. So I believe the higher midterm scores were 35%, lower midterm scores were 25%. So there's a 10% difference between them. Okay. So if you scored better on midterm 2 than you did on midterm 1, I kind of swapped that into the grade for midterm 1, and then your midterm 1 grade is now what you got for that. So I haven't found an elegant way to do this on Canvas, and so I just do it manually. So if you're confused about, oh, why did I get the exact same score for midterm 2? It's like, well, you might have, and there actually was one person who got the exact same score in both exams. But for most of you, if you did better on midterm 2, that now is counting for a higher percentage. So that's in the midterm 1 slot on Canvas. Okay. If you did worse on midterm 2, then it's just in the midterm 2 slot. Okay. All right. So I have the exams for you guys to pick up today. If you have any questions about how it was graded or anything like that, just like the first exam, I try to leave as many comments as I could. Definitely ask me for clarification. I'm happy to provide. Okay. Okay. All right, and so with that, we are, most of the semester is now really in the books, and so the last kind of piece of business that we have to do is just the final project. And so to do the final project, you're going to need to understand isoparametric elements, and so that's what we're going to do today. We may have a little bit spillover on Tuesday, but I don't think we have another full lecture in me. So today is going to be a full lecture, and then whatever we don't finish today, we'll finish on Tuesday. The rest of the time for this semester is just going to be just open office hours for you guys to work on your projects. Okay. Now I know quite a few of you have already started working. You've already, some of you have already emailed me questions. So keep them coming. I think that's kind of the easiest way for me to answer you guys' questions, just because you guys are grad students, and so I know scheduling is always a bit tough. So whenever time you have to work on it, and if you run into issues, just send me an email. I'm always happy to look at your code and provide hints. Okay. Now I'm not going to write your code for you, so don't send me a problematic code and expect me to fix it, but I will give you guidance and give you feedback in terms of what I'm seeing. Okay. Okay, good. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and pick up where we left off. Okay. So we kind of left off at not very an ideal place. So let's spend some time kind of reminding ourselves kind of what we went over last time. Okay. All right. So the goal of isoparametric elements is to basically give us a way to perform all of the integrals for 2D heat conduction. Okay. Okay. All right. So our starting point for our discussion today is going to be the weak form for 2D heat conduction. Okay. So we have double integral gradient of your weighting function multiplied by the thermal conductivity multiplied by the gradient of the temperature, dA. Okay. So that right there is our double integral with balanced derivatives. And so we can see both our weighting function and our temperature function here have first order gradient derivatives. Okay. This is equal to double integral of our weighting function multiplied by our thermal generation term. Okay. Right. So that's a term that's going to end up on the right-hand side of our equation there. Okay. That's going to contribute to our weighting function, or excuse me, to our element forcing vector. Okay. Plus, we're going to have a contribution from the Neumann boundary conditions as well. Okay. All right. So plus line integral around the boundary of our weighting functions multiplied by q bar ds. Okay. So this last term right here, this is our Neumann boundary condition. All right. So essentially, in order for us to apply our finite element form, we have to evaluate this integral expression here. So we have to compute these three integrals, but we have to do them on an element that may have an arbitrary shape. Okay. So the challenge, evaluate all these integrals. on elements with arbitrary shape. Okay. All right. Maybe it's not completely arbitrary, right? So we at least know for a fact that our elements will be quadrilaterals. And so there'll be four vertices and four sides. It's just that they may be oriented in kind of a strange way. Okay. And so that's a challenge, especially when every element in your system will look slightly different, right? So for those of you who've kind of already started the project, you may have seen this already, where the triangles on the mesh, right? They all don't look the same. And so they have different vertices, they have different locations, they have different sizes, right? But, we want to compute these integrals in a way where, it's our algorithm is general enough so that we can handle any kind of orientation for the element that we have. Okay. So the solution to this, the solution to this challenge here is to do basically a Gauss quadrature. Okay. Right, so our Gauss quadrature, that's typically how we like to perform integrals numerically because it's very accurate for polynomials. Okay. Now, but the problem with Gauss quadrature is that it requires a very strict, our integration bounds have to be between -1 and 1. Okay. Right, which generally is not going to be true for an arbitrary element, right? That's oriented arbitrarily in space. So we need a solution to the solution, right? So we came up with one solution, it came up with another problem. So our solution two, okay, our solution two is going to be the same approach that we did in 1D, where when we wanted to apply Gauss quadrature and our integral was on arbitrary bounds, we had to do a change of variables in order to change those bounds into what we want. Okay. But a change of variables in 2D is a bit more complicated when you're changing kind of both variables at the same time. And so this technique that we're doing of changing variables in multiple dimensions, two dimensions at the same time, is called isoparametric elements. Okay. And so that's kind of what we were in the middle of going over on Tuesday. Okay. Okay. So the isoparametric approach, it's going to seem very overwhelming just because there's a lot of steps in it. There's a lot of linear algebra that we have to do. But the hope is that, by the time we finish going over it, you're going to have a very kind of structured and very clear algorithm that you're going to implement into your final project. Okay. So the way I'm going to present this, I'm going to go through the derivation. So we kind of got halfway through the derivation last time. And then we're going to take that derivation and turn it into an algorithm or basically a step-by-step, recipe for what you need to do, and then that step-by-step recipe is what you're going to apply in your final project. Not necessarily in part A, although you can do it in part A, but in parts B and C, you're going to apply this method. Okay. Okay. All right. Any questions? So this was just kind of a recap from last time. Any questions on this so far? Okay. All right. So let's pick up where we left off last time. Okay. All right. So last time, let me just kind of scroll up here a little bit. Okay. Actually, let's start down here. Okay. So where we're going to start here is actually with the element stiffness matrix. Okay, so our element stiffness matrix is comprised of this term right here. where the main issue that we were dealing with is the fact that these gradients, right, the gradient of W, the gradient of T, these are gradients which had derivatives in the physical domain, right? So partial X, partial Y. Partial partial X and partial partial Y. Okay. But we don't want that, right? So we don't want to have derivatives in the physical domain. We would rather have our derivatives be in the parent domain, right? So partial partial epsilon, partial partial eta. Okay. So partial partial epsilon and partial partial eta. Okay. Okay. So we were in the process of converting those gradient terms, into the derivatives that we want. Okay. Okay. So for instance, right? So after we apply our shape functions and after we kind of plug in for the nodal solutions, right? Remember, our gradients usually take the following form. Okay? So for instance, the gradient of t, right? So this is after applying our shape functions. Okay. All right, we end up with a situation like this. And so our gradient of t is, and remember, when you apply shape functions and when you apply the nodal solutions, any derivatives that you're going to take get shifted onto the shape functions themselves because the nodal solutions don't depend on anything. They're essentially constants. But our shape functions do vary in space, at least within the element itself. Okay. All right. So we have partial n1, partial x, partial n2, partial x, partial n3, partial x, partial n4, partial x. Okay. And remember, for this discussion here, we're working with the four-node quadrilateral. Okay, so that's why there are four shape functions here, because there has to be one for each node. Okay, and then we have the y derivatives as well on the second row. So we have partial n1, partial y, partial n2, partial y, partial n3, partial y, partial n4, partial y. Okay. All right, and this is multiplied by our vector of nodal solution. So this is multiplied by T1, T2, T3, T4. Okay. Okay. And then you can come up with the corresponding kind of expression for gradient of W as well, but it's just the same shape function derivative. So I'm not going to write the same thing again. Okay. All right. So with this expression here, the nodal temperatures are fine, right? So this is good, right? So these are just nodal values, right? We don't need to change anything there because that's always going to be the same. Okay? Remember, the issue of what we have is with everything in here, right? Because these are derivatives in space. Okay. Okay. So basically, we need to plug in for this for an expression that has shape function derivatives in the isoparametric domain. Okay. So what is that going to look like, right? So if you remember from last time, what we said was that, we found our Jacobian, right? So the Jacobian is it has our derivatives of our spatial coordinate functions here. So this is partial x, partial epsilon, um, partial y, partial epsilon, partial x, partial eta, partial y, partial eta. Okay. Okay, so this is something that you can compute right away, right? So this is something that only really depends on the nodal positions. Okay. All right, and so what we said was that, we can take this, we can perform a little bit of a suspicious ghetto math here, right? And so if we take the inverse of the Jacobian, right? Inverse just essentially means you're taking 1 over that. And so basically we're going to say that if we take the inverse, all of our derivatives are going to swap, swap sides, right? And so the denominators will become the numerators, okay? Right, and so this will be partial epsilon, partial x, partial eta, partial x, partial epsilon, partial y, partial eta, partial y. Okay. Okay. So why is that significant there? So we can combine this, right? We can combine this Jacobian inverse together with a matrix of our shape function derivatives in the isoparametric domain. Okay. Okay. And so I don't think I got a chance to write this last time. So let me actually write out all the shape function derivatives here. Okay. So there's 8 of them, and so it is a little bit tedious, but let's write them out just for the sake of completeness. Okay. So you have partial n1, partial epsilon, right? This is equal to minus 1/4 times 1 minus eta. Okay. Partial n2, partial epsilon. Okay. 1/4 times 1 minus eta. Partial n3, partial epsilon. This is going to be a 1/4, 1 plus eta, and then partial n4, partial epsilon. This is a minus 1/4, 1 plus eta. Okay. Okay, and then we have all the eta derivatives as well. So partial n1, partial eta is equal to minus 1/4, 1 minus epsilon, partial n2, partial eta is equal to minus 1/4, 1 plus epsilon, partial n3, partial eta is equal to 1/4, 1 plus epsilon, and then partial n4, partial eta is 1/4, 1 minus epsilon. Okay. All right. So a little bit tedious, I know. Okay. But remember, the whole point of this is that, we've gone through the trouble of swapping from the physical domain to the isoparametric domain. And within the isoparametric domain, we know the exact size and we know the exact bounds of our element, right? So our element is going to be between -1 and 1 in the horizontal direction. That is our epsilon direction. And it's going to be between -1 and 1 in the vertical direction. That is our eta direction. Okay. And so from that, we know exactly where all the vertices are, so we can compute the shape functions. And then from those shape functions, we can compute the shape function derivatives. Okay. So basically all these are exactly known, which is the whole point. Okay? right? So this is kind of the huge motivating factor why we want to go through this because we don't know, right? So if we go back to our original gradient of t, we don't know what partial n1 partial x is going to be for a generic element, right? But we know exactly what partial n1 partial epsilon is going to be because we know what our isoparametric element looks like, okay? So the goal, right, is to take these shape function derivatives in the physical domain and put it in terms of these, but we recognize that there's some kind of conversion factor that we need to do. Okay. Okay. All right. So now that we have kind of established these shape function derivatives, and now that we've kind of established that all of these are known, right? Let's take one shape function derivative in the physical domain, and let's see how we can write it in terms of its counterpart in the isoparametric domain. Okay. Okay. So let's just do a quick example here. Okay. So let's say we have partial n1 partial x, right? So this right here, derivative of a shape function in the physical domain. Okay. All right, so we can use kind of a kind of like a chain rule. You can think of like a chain rule from calculus, where we can say this is equal to partial n1 partial epsilon, okay, multiplied by partial epsilon partial x, okay, plus partial n1 partial eta partial x, right? Okay. I shouldn't say it's kind of the chain rule. It's exactly the chain rule actually, because x is a function of epsilon and eta, because that's part of the change of variables that we're doing. And so if we take the derivative and we chain it out, this is what we obtain. Okay. Okay. So it might seem like we made this situation worse, right? So we took a single derivative and we turned it into four, right? So that sounds like four times the problem. But let's inspect every term on the right-hand side here, and let's see if we know these or not, right? Okay. So first thing we notice immediately is that we have the derivative of the shape function with respect to the isoparametric variables, epsilon and eta, okay? We have those. In fact, they are just right here, right? So that's this expression here and this expression right here. Okay. So these are good, right? So we know these, and so we can plug in for that very easily. Okay. The other part of this is basically these conversion factors, which are the derivatives of the isoparametric coordinate with respect to the physical coordinate. Okay. We have these two. In fact, they were just right hanging out right above here. Okay. So we have this one here and this one here. Okay. Now, those values are inside our Jacobian inverse, but these are also known as well. Okay. So that's great, right? And so, we chained this out. We thought that we were creating more problems, but we took something that we didn't know and we're now expressing it in terms that we do know. Okay. So let's combine these two together, right? Just recognize the fact that our physical shape function derivatives are just going to be the combination of our isoparametric shape function derivatives and our Jacobian inverse. Okay. And let's put it in matrix form so that it applies equally to every single shape function in our in our domain here. Okay. Okay. All right. So I'm going to write out the full expression here, but I'm going to shorten it after this. And so this will be kind of the only time you see the full thing. It's going to take me 10 minutes to write this whole thing. So, you guys better appreciate it. Okay, so first we have the shape function derivatives in the physical domain. So we're going to repeat that here. So partial n1 partial x, partial n2 partial x, partial n3 partial x, partial n4 partial x. Okay. And we have all the derivatives in the y direction as well. Okay. Okay. All right, so everything on in that matrix there, we don't explicitly know, but we do know that it can be comprised of the two components that we talked about above here. Okay. All right, so first thing is we're going to have a 2 by 2 matrix here that's going to be our Jacobian inverse. Okay? This is going to be partial epsilon, partial x, partial eta, partial eta, partial x, partial epsilon, partial y, partial eta, partial y. Okay. We're going to multiply that by a row matrix, right? So a matrix that has two rows and four columns of our shape function derivatives in the isoparametric domain. Okay. Okay, so we're going to multiply this by partial n1, partial epsilon, partial n2, partial epsilon. Okay. Partial n3, partial epsilon, partial n4, partial epsilon. Okay. Partial n1, partial eta, partial n2, partial eta. Okay. All right, so let me zoom out here just so you can kind of see it all in its glory. Okay. Okay, good. So again, this expression here is it's a lot of math, right? It's a lot of linear algebra. But remember, we're not setting this up for something that we're going to compute by hand. We're essentially setting this up for something we're going to compute in the computer, right? And so basically what you're going to see is that, when we actually do these in code, right, we're going to establish these matrices. So we're going to have MATLAB compute these for us, and then we're going to have MATLAB do the matrix multiplication, okay? And so you can see this first matrix right here, this is our Jacobian inverse. Okay. Right. And this right here is our shape function derivatives in the isoparametric domain. Okay. And just for the sake of argument here, I'm just going to call it a matrix. I'm just going to give a shorthand for it. Okay. So my shorthand notation for that is going to be partial ni partial epsilon j. So just so I don't have to write out the full matrix. Okay. All right. Good. So this is great, right? And so now that we have an expression that we can plug in the right-hand side here, we can plug this back into our weak form and replace all those physical shape function derivatives. Okay. Okay, so that'll be kind of the last thing that we do. Okay. Okay. So it's a lot of matrices, a lot of derivatives there. Any questions on this before we kind of plug it all back in, we put it all together? Okay. Okay, so let's go ahead and plug everything back in and you'll kind of see how this kind of all comes together. Okay. Okay. So let's go back to where we started, right? So we started from this expression here, right? So we double integral gradient of w times k times gradient of t dA. Okay. So that right there is a generic double integral on a generic 2D domain. Okay. First thing I'm going to do, first step we're going to do is we're going to convert the integration bounds, right? Because we can't do Gauss quadrature if our integration bounds are arbitrary. Okay. So first thing we're going to do is we're going to convert So we're going to convert our integration bounds to -1 and 1. So this step right here is going to convert integration bounds. Okay. All right, and then we're still going to have our shape, or we're going to still have our gradients, and so we're going to plug those in for those next, right? But right now, this gradient of W, gradient of T, those are still in the physical domain, but that's okay. 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 And remember, when we're converting our integration bounds in 2D, our conversion factor is the determinant of the Jacobian. Okay. Right. So this determinant of the Jacobian is the conversion factor that we multiply to account for the changing bounds. Right. So it's a little bit different in 1D. So remember, in 1D we had, we just converted one variable, and our Jacobian was just a single value. And so remember, we multiplied by the Jacobian to do that conversion. Okay. And since we changed our integration bounds, we're integrating over epsilon and eta. Okay. All right, so we've converted our integration bounds. We have that determinant of Jacobian that comes out from the changing of the bounds, right? Next, we're going to convert our derivatives, or I should say plug in for the physical derivatives. Okay. All right, so essentially we're going to plug in this expression that we found up here. Okay, okay, so this is going to be equal to integral from -1 to 1, integral from -1 to 1. Okay. First, we're going to plug in for gradient of W here. So for gradient of W, we have, right, we have partial Ni, partial epsilon j, multiplied by the Jacobian inverse. Okay. So this right here, this is our gradient of W, right? It used to have physical derivatives. Now it has derivatives in the isoparametric domain or the parent domain, okay, because of the shape functions and because of the Jacobian inverse. Okay. All right, next we have K. Technically, K can also be a function of X and Y, and so that's something you have to consider here. But for the project, I think for the project, I just set the value of K to be constant, and so we'll just assume that here. Okay. So K is just a constant, it's just kind of along for the ride. And then we're going to multiply by the same thing, but for the gradient of t, right? Which is, we're actually going to reverse the order here. So we have Jacobian inverse times the shape function derivatives in the parent domain, the partial Ni, partial epsilon j. Okay. So this right here is gradient of t. Okay. Next, we're going to multiply this by the determinant of the Jacobian. So that just comes right down from up here. Okay. And finally we have our integration variables d epsilon d a. Okay. Or you can do d eta d epsilon. It's the same. All right. So quite the doozy, but this expression right here, let me kind of box this because this is kind of a good stopping point here. Okay. So I know it looks like a mess, and it kind of is a mess. But trust me when I say that, every single part of this integrand here, we've eliminated x and y, right? So we've eliminated x and y in terms of the integration variables, and we eliminated their derivatives as well. Okay. So this expression that I boxed here is directly able to be used with Gauss quadrature. Okay. All right. So this is what you would do. So I know I said already that you can do part one without this, right? And so if you want to just do part one directly from the triangles, you can definitely do so. But if you wanted to compute part one using Jacobians and all this stuff, this is how you would do it. Okay, so this is part one of the project. All right. Cool. All right. Any questions on how we got to this point here? Okay. Good. All right, so next, now that we have our element stiffness matrix, right? So this right here will form our element stiffness matrix. Let's go over the element forcing vector, right? And we'll do it in two parts. And so we'll do the body forcing term slash the thermal generation. So that'll be part two of the project, and then we'll go over the Neumann boundary condition will be part three. Okay. Okay. So let's do thermal generation first. And so this is going to contribute to the element forcing vector for each of our elements. Okay. All right, so thankfully, the process of applying isoparametric elements here is not nearly as involved. It's not going to be a full lecture of derivations here. Okay, but let's go over it. Okay, so the contribution to the element stiffness matrix, or excuse me, element forcing vector from the thermal generation term looks like the following. Right, so we're gonna have a double integral of W times S, which is a function of X and Y, d. Okay. Right? So we have a generic double integral that's integrated over the entirety of the area of the element of our weighting function multiplied by our thermal generation term. Okay. Okay, so first thing we do when we apply the finite element form is that we essentially replace our weighting function with a vector of our shape functions. Okay. Okay, so first thing is we take W here. Okay. Right? So remember, W is approximated. W is comprised of our shape functions. And so let's go ahead and do that. Okay. So we have N1 of X and Y, and 2 of X and Y, and 3 of X and Y, and 4 of X and Y. Okay. Okay. All right, so this result here makes sense because for every element, this is contributing to our element forcing vector. And so there should be 4 entries in this vector for us to contribute, right? So each entry in that vector corresponds to each of the different shape functions. Okay. Okay. But this is not something that we can use right now because in order to perform this integral, right, this integral is technically still in the physical space. And so we also want to convert this integral to the isoparametric space so we can perform Gauss quadrature. Okay. Okay. So this step is a little bit more subtle. So in order to do this, we need to replace x and y with expressions that have epsilon and eta. Okay? So if you recall, kind of very early in the process, right? So this is kind of what we did last on Tuesday, was we define, okay, we define these two coordinate functions here. So x of epsilon and eta and y of epsilon and eta, these are our coordinate functions. Okay. So you can think of it as kind of a conversion from x and y to epsilon and eta. Okay. So remember, we did this conversion with our shape functions, and so we said that x of epsilon and eta is x1 times n1 epsilon and eta plus x2 and 2 of epsilon and eta plus x3 and 3 epsilon and eta, and I ran out of room, plus x4 and 4 epsilon and eta. Okay. Same thing for y, right? So remember, x1, x2, x3, x4, these are the x coordinates for every node in our original element. Okay. Okay. So again, these look like pretty gnarly expressions, and they are, not gonna lie. But eventually, we're going to be using this with Gauss quadrature, and so again, this is something that looks kind of nasty here, but once you kind of program it and you kind of systematically compute them with the loop and variables, this ends up being very easy to do. Okay. Okay. So first thing is we're gonna plug in, right? So basically, everywhere we see x and y in the original, in the original, body forcing term, we're going to plug in x and y here. Okay. Okay. We're going to plug these in right here. Right, so your body forcing term is going to be some function of x and y, and so you can plug in these expressions for the coordinate functions to essentially create functions of epsilon and eta instead. Okay, that's also going to convert our shape functions, and so our shape functions now are going to be functions of epsilon and eta. Okay, and then we also need to add in our determinant of the Jacobian as well, right? So that's going to be a factor that we're going to multiply just so that we can convert our integration bounds to -1 to 1. Okay. Okay, so put all that together, we end up with the following expression. Okay? So this expression here is kind of the crux of part 2 of the project. Okay. So after converting all of those, we have integral from -1 to 1, integral from -1 to 1, right? So that's our Gauss bounds. Okay. Then we have our 4 shape functions as functions of epsilon and eta, right? So remember, we know these, right? So these are known functions that we've already computed because we know what our element looks like. Okay. Okay. Next, we have our thermal generation term S, right? Where we replace x and y in our function there with their coordinate functions, right? So this is now S of x of epsilon eta and y of epsilon and eta. We're going to multiply that by the determinant of the Jacobian. Okay. And we're integrating over epsilon and eta. Okay. Again, I know it looks gnarly, but then, once we kind of get into the algorithm, you'll see that it's, hopefully it's not too bad. Okay, any questions on this?
Yeah, you said we know what the shape functions look like. Where's that established?
Yeah, great question.
That's what I forgot.
Yeah, no, for sure. I think it was quite a while ago. We definitely haven't written them today. And so, remember, we're working in an isoparametric space here. So, we're looking at basically this is epsilon and eta space. Okay. And, we've kind of established that in the isoparametric space, we're going between -1 and 1. So our element itself looks like this. Right? So this is -1, 1, -1, and 1. Okay. So now here is node 1, node 2, node 3, and node 4. Okay. Where the location for node 1 is -1, comma, -1. Location for node 2 is 1, comma, -1. Location for node 3 is 1, comma, 1. And location for node 4 is -1, comma, 1 here. Okay. All right, so the shape functions, they're functions of epsilon and eta. They're kind of based on this image here, right? And they're kind of based on the real way that we obtained these was we could solve a 4x4 system of equations for, the four nodal solution values, right? But I think the easier way to kind of do it is to just work off the principle where if you evaluate the shape function at that node, you should get 1, right? So when you evaluate n1, right? So node 1 is in the bottom left. And so when we plug in -1, -1 in for n1, we should get 1, right? Okay. So knowing that, knowing the coordinates for our nodes here and knowing the size of our element, our shape functions can be written as the following. Okay, so n1 of epsilon and eta is 1 over 4 times 1 minus epsilon, 1 minus eta. Okay. Right, so you can plug in epsilon is equal to -1, eta is equal to -1. You can see that we get 2 times 2, which is 4, divided by 4, which is 1. Okay. You plug in any other coordinate. So let's say you plug in the coordinates for node 2, you're going to get 0, right? Node 3, 0, node 4, 0. Okay. All right, n2 of epsilon and eta, right? That's going to be a 1/4, 1 plus epsilon, 1 minus eta. Okay. And 3 of epsilon and eta is equal to 1/4, 1 plus epsilon, 1 plus eta. And 4 epsilon eta is 1/4, 1 minus epsilon, 1 plus eta. Okay. Yeah, so those are our 4 shape functions, right? And the thing to kind of note here is that, because we have the 4-node quadrilateral, we have the presence of that mixed term, of that pseudo-linear term. So if you multiply the last 2 terms in each of the foiled expressions, you'll see that you get epsilon eta, either positive epsilon eta or negative epsilon eta, right? So that's a property that's unique to the quadrilaterals, that we have that mixed term there. For the triangle, you don't have that. So for the triangle, when you take derivatives, you just end up with a constant. So in that sense, your project is a little bit simpler just because you don't have to, your derivatives are simpler. But for this one, you have that mixed term there. Yeah. Yeah, good question. We haven't established that today. All right, any other questions on this part here? Okay. All right, so that's part 2. So part 2, you're basically gonna be tasked with evaluating this integral here for every single element. Okay. All right. And so the last part of our weak form, so we kind of go all the way back to kind of where we started today. The last part of our weak form is computing the Neumann boundary condition term. Okay. And this is part 3 of the project. Okay. Now, this is going to make part 3 seem very simple, but what makes part three difficult in the project is not necessarily the integral that you're computing. The integral is actually quite simple. It's just the details in terms of how you determine, where the Neumann boundary is. So this is going to make part three very simple, but the challenge of part three is in the programming. It's not necessarily in the math or the logic here. Okay. Okay. All right, because the integral we are evaluating is actually quite simple. So we have a closed integral here. So this is a line integral. Okay. Specifically, this is a line integral only on the locations where the Neumann boundary condition is present. Okay. And that's actually the hard part, is determining where the Neumann boundaries are. But mathematically, it's quite simple. So we're basically just taking our same vector that we use for the thermal generation terms. We have N1, N2, N3, N4. Okay. Multiplied by Q bar ds. Okay. Where Q bar there, that is our Neumann value. And for the project, we're going to keep things simple. And so we're not going to have a spatially varying Neumann value. The Neumann values are just going to be constant. Okay, so you don't have to worry about actually integrating anything here. Okay. All right, and so the only thing we have to do here is we just have to convert the integration bounds into a Gauss quadrature. So the good news about the Neumann boundary condition is that we're no longer doing a double integral anymore. This is a one-dimensional integral, right? So a line integral is just a 1D integral. Okay. So the Gauss quadrature we're going to do is also 1D. Okay. Now we do have to do a change of variables because this integral is not within -1 to 1. So we are going to have to do a change of variables, but the change of variables is actually quite simple. Okay. So this is going to convert to integral from -1 to 1 of our four shape functions in the isoparametric domain. So N1 epsilon eta, N2 epsilon eta, and 3 epsilon and eta, and 4 epsilon and eta, okay, times Q bar, right? We need our conversion factor. So the conversion factor in this case is just the one-dimensional Jacobian, right? Which in 1D is actually quite simple. Right? So the one-dimensional Jacobian is just going to be the length of the element divided by 2. Okay. So this LE right here is the length of the element's edge. Okay. And this entire term right here, this is our 1D Jacobian. Right? Right. So remember the purpose of the Jacobian is the fact that, when we're changing variables, our integration domain may be compressed or it may be expanded. So this is kind of it kind of accounts for the change in length of the domain. Okay. Okay. D epsilon. Okay. So again, with part three of the project, the integral itself, quite easy. Getting to this integral and computing things correctly on the correct edge with the correct nodes and the correct elements, that is going to be the hard part. And so, I think in the project specs, I think I wrote quite a bit on part three to kind of help you establish that. There's quite a bit of hints in the template code as well, starter code. But still, I think this is the part that I think people kind of struggle with, just with the logic. Okay. So don't be afraid to reach out for help on part three, because it can be confusing, and there's multiple kind of traps inside there as well. Okay. All right. Any questions on this? Okay. All right, so for the last 20 minutes today, we're going to start writing down what I call the isoparametric algorithm. Okay. So this is kind of a step-by-step process on how to actually implement the isoparametrics. And so this will be good for part 1 and part 2 of your project. Okay. So this is kind of a good step-by-step to do. Okay. We may not finish it today just because just because we're probably gonna run out of time. So whatever we don't finish today, we'll finish up on Tuesday. And I do actually have an example for this as well. So we'll apply the isoparametric algorithm to just a very simple element, just so that you can kind of see the calculations in action, just to kind of give you a grounding sense for what to expect for the project here. Okay. 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 So again, this isoparametric algorithm, I've kind of written it in the style of a pseudocode, right? So pseudocode, if you're not familiar, is not real code, right? So I'm not going to be writing MATLAB statements here, but these are statements that kind of describe the logic and describe kind of the actions of the code that you are going to write, okay? So the idea is that each step in this algorithm right here is going to correspond to, maybe 1, 2, 3, 4 lines of code that you would write in MATLAB, but it would follow the exact same kind of order of operation, the exact same procedure. Okay. Okay. All right. So to help illustrate this, we are going to do, an example. This is not the example I was talking about, but this is just kind of something just to help kind of illustrate for this. Okay. So let's write the algorithm for the 4-node Gauss rule or 4-point Gauss rule on a quadrilateral. Okay. Okay, so just to kind of refresh your memory, right? So for a 4-point rule, right? The Gauss points are the following. Right, so let's say we have our element here. Its upper and lower bounds are -1 to 1, right? The first Gauss point is right here. Okay. So this right here is GP1. Okay. The coordinates for this point right here is -1 over √3, comma -1 over √3. Okay. Next, we have GP2 here. Okay. Coordinates for this node right here is a +1 over √3, comma -1 over √3. Okay. Next, we have Gauss point 3 right here. So this is +1 over √3, +1 over √3. Okay. And then we have GP4. This is -1 over √3, +1 over √3. Okay, so we want to do Gauss quadrature using the isoparametric approach. Okay. Okay. All right, so let's write kind of step by step here for the algorithm here. Okay. So the most efficient way to do Gauss quadrature in code, right, especially when you have multiple Gauss points like this, is to write a loop. Okay. So first thing is we're going to have a loop. Okay. So for your case in MATLAB, this is going to be a for loop. Okay. And the loop is going to loop over each of the Gauss points. Okay. Right, so we're going to do a separate calculation for each Gauss point here. So you can think of it as, we're going to visit each one of these. So first, we're going to visit this Gauss point. That's going to be the first iteration of the loop. Second iteration of the loop, we're going to visit that Gauss point. Third iteration, and then fourth iteration, okay? And each time we visit a Gauss point, we're going to compute each of their contributions to the element stiffness matrix and the element forcing vector, and then add them together at the very end, okay? Okay. All right, step 1. Right. First thing to do when you enter the loop is you have to establish the value of the Gauss coordinates. Okay. right? Because we're essentially going to be evaluating each of our integrals, right? The element stiffness matrix integral and the element forcing vector integral at each of the Gauss points, right? And so we're going to plug in for epsilon and for eta, right? So think of this as establishing the values of what you're going to plug in for epsilon and eta, okay? So we have epsilon g, okay, and eta g, okay? Sure, let me do it like this. I think that's fine. Okay, so for example, on the first iteration of the loop, okay, so on the first iteration of the loop, we're going to plug in epsilon g, right? So you're just going to have a simple statement, epsilon g is equal to minus 1 over root 3, and eta g is equal to minus 1 over root 3, okay? Because we're basically taking, we're saying that we're visiting this Gauss point right here, so Gauss point 1, and we're plugging those values in for epsilon g and eta g. So from here on forward, we've plugged in, we've established the values of our Gauss point, and everywhere we see epsilon and eta in our expressions and our formulas, that's exactly what we're going to plug in. Okay. Step 2. Step 2 is we're going to compute the values of the shape functions at these Gauss points. Okay. All right, so now that we know what to plug in for epsilon and eta, right, we're going to plug those in to compute the values of the shape functions, right? Because if you look back, right, just a little bit here, right, we have integrals like this where we have to plug in values for the shape function, n1, n2, n3, n4, right? So let's just go ahead and plug in for that right away here. Okay, so for n1, right, right, so we have our formula for n1, which we went over earlier. We're going to plug in for epsilon g and eta g. This is 1/4, 1 minus epsilon g times 1 minus eta g. Okay. And 2 of epsilon g eta g. Okay. 1/4, 1 plus epsilon g, 1 minus eta g. And 3 of epsilon g eta g. So this is 1/4, 1 plus epsilon g, 1 plus eta g. And 4 epsilon g eta g. Okay. 1/4, 1 minus epsilon g, 1 plus eta g. Okay. Okay. So those are our formulas for the 4 shape functions. But since we're plugging in for epsilon g and eta g, realize that you're going to get explicit values for this. Okay. All right, so these will be variables that you save within the loop itself. Okay. Now the exact values of these shape functions will change from loop iteration to loop iteration because the values of epsilon g and eta g are going to change, right? So we're going to move on to different Gauss points. But these need to be computed, especially if you're computing the element forcing vector. Okay, good. All right, step 3. All right, now that we've computed the shape functions at the Gauss points, or at this Gauss point, Let's now compute the shape function derivatives at the Gauss point. Okay. All right, so one thing you should see from the step-by-step here is that, basically every kind of matrix and every kind of value that we've established in the derivations up until this point, we basically just need to compute them explicitly. And since we have our Gauss point here, we've kind of already established that in step one, we should be able to compute everything that we need because anywhere we need epsilon and eta plugged in, we just plug in our epsilon and eta from this particular Gauss point. Okay, so let's go ahead and plug in for that. So we have partial n1, partial epsilon is equal to minus 1/4, 1 minus epsilon g. Okay. Partial n2, partial epsilon is equal to a positive 1/4, 1 minus eta g. Okay. Partial n3, partial epsilon is equal to 1/4, 1 plus eta g, and then partial n4, partial epsilon is minus 1/4, 1 plus eta g. Okay. And then we have all the eta derivatives as well. So we have partial n1, partial eta is equal to minus 1/4, 1 minus epsilon g, partial n2, partial eta is equal to minus 1/4, 1 plus epsilon g, partial n3, partial eta is 1/4, 1 plus epsilon g, and then partial n4, partial eta is equal to 1/4, 1 minus eta g. All right. So what you're going to see, for your project, step 3 is going to be a lot simpler because, the shape functions for the 3-node triangle, they don't have any cross terms. And so all of your shape function derivatives are actually just going to be constant. They're actually either going to be 1, -1, or 0, right? So I think that's the part that kind of gives people pause about the project is that, step 3 is actually quite simple. But for a 4-node quadrilateral, this step is a little bit tedious because, these shape function derivatives are still functions of epsilon and eta. Okay. All right. Any questions on this so far? Okay. Good. All right. So now that we have the shape functions, we have the shape function derivatives. We're just going right down the line of things that we need. So next thing that we need is we need to compute the corresponding physical coordinates of this Gauss point. Okay. So remember, we're performing a change of variables here, right? So we're performing a change of variables from the physical domain to this isoparametric domain, right? But these Gauss points, right? So even though we know their values, right? So they're the minus 1/√3 plus 1/√3, that was mapped originally from some physical point in the physical domain. Okay. So we need to compute what that is based on our shape function value that we've already computed and based on the coordinates of the node in the physical space. Right? So that makes it sound very complicated, but we've actually already seen this expression here. Okay? So this is basically just computing the function x of epsilon g, eta g, okay? Right, so remember we wrote this expression back when we were talking about part 2 earlier, right? So x of epsilon g, eta g, this is just going to be our 4 nodal coordinates, x1, x2, x3, x4, multiplied by the corresponding shape functions, but the shape functions we're evaluating at the Gauss ones, which we already computed in part 2 up here, okay? Okay, so just to kind of put it plainly here, this is x1 and 1, epsilon g, eta g, okay, plus x2 and 2, epsilon g, eta g, plus x3 and 3, epsilon g, eta g, plus x4 and 4, epsilon g, eta g. Okay. Right. Where each of these shape functions, so n1, n2, n3, n4, right? We've already computed these, so these were computed in step 2. Okay. Right, so you can kind of see why we computed the shape function values first, because we used it right away. Okay. And then these x1, x2, x3, x4, right? This is information that you can often read directly from the mesh. Okay. Okay. So I think for the project, for those of you who have kind of already gotten started on the project, right, there is a matrix that's already established for you from the mesh called the nodes matrix, right? That nodes matrix contains all the XY coordinates for every single node in the mesh, right? So you just have to refer to that matrix and you have to refer to the correct nodes for that one. Okay. Okay, and then last thing I'll write down before we end for the week is the same function for y, because we need it as well. Okay. So you have y of epsilon g, eta g. Okay. It's going to be y1, n1, epsilon g, eta g, plus y2, n2, epsilon g, eta g, plus y3, n3, epsilon g, eta g, plus y4 and 4, epsilon g, eta g. Okay. Same thing for this y function here. So for the y function, our shape functions, we already computed in step 2. All the y nodal values, we read that directly from the mesh itself. Okay. So now after we've done step 4 here, whenever we see a function here that has x and y, most notably in part 2, so step 4 here you're going to use in part 2 mostly, we're going to plug in these expressions here, okay? And once again, these look like scary expressions here, but remember, everything in this expression is known, right? So all the x coordinates are known. We've already computed the values of the shape functions already in step 2, right? So even though these expressions are scary, you should get an explicit singular value for x and y after applying these formulas here. Okay. So it's going to look like a complicated expression, right? And a lot of things you're going to write in code are going to have these kind of complicated expressions. But just know that once you plug everything in, they should have a single value. Okay. And that's kind of the power of using programming like this. And so, what you can take complicated expressions, and after you compute them, they're stored as a single value in a variable that you can use later on. Okay. All right. Any questions on this before we wrap it up for the week? Okay, all right. So that's all the time we have for today, and so we'll pick this up on Tuesday. So we'll finish up talking about the algorithm on Tuesday. I have an example which kind of runs through these calculations, and then from there we're just working on the final project. Okay. All right. So thank you guys for coming today. If you guys are going to the alumni event, I'm going there right now, so we can all kind of go together. But if not, I will see you guys next week. Oh, midterm. Yes, I'm sorry. Totally forgot about that. So I did something a little bit differently this semester. I did place more weight on the exams than I usually do, just to kind of try it out. Let's talk kind of offline, and then we can see. Yeah, so I know some people are in that position. I don't want you guys to feel like final project is useless. Yeah, let's send me an email, and then we can set up a time to talk next week about it. Yeah.
Is it projects? Is it like once you get to it?
I would say part one, part two are fairly straightforward. So those parts, you kind of just go right off the algorithm. As long as you just kind of, what to implement. Part three is a bit more challenging just because it's the way it's implemented is just kind of difficult. But the majority of the points are going to be part one. So I'd say if you do well on those ones, but important to do a project, and then whatever you can do in part three is good. There's a part people work, but part four is just applying your code from parts one and two to like a arbitrary.
Guess the values are sort of like, wait, once you get down to it, it's sort of plug them in.
Yes, if I could grab it.
Yes, yeah.
We'll see.
We'll see. We'll go over it more.
Oh,
okay.
yeah.
We'll finish the algorithm on Tuesday, and then we'll kind of talk about.
Are you going?
It's implemented.
I'm going to see who's there real quick.
Yeah.
Yep. Get out of here.
Oh, okay.
John. Hey, Professor?
Yeah.
James said the event, he asked if either of us, you or me, could
Yeah.
drop this off.
Okay, yeah, I can bring it.
I wasn't sure if you wanted to hold on to it or.
Why don't you hold on it, because I might be talking to other people too.
Yeah. He had set up the rocket.
Oh, okay.
Event, so he's like,
Yeah, makes
"Can you
sense.
grab that for me?"
Yeah.
See if he